Hi, and today we'll be going over another really important Algebra 1 topic that shows up all the time in homework and problems and that I've had experience with tutoring people with. And that's solving simultaneous equations, or solving linear equations. Essentially, you're given two lines, and you're asked where they intersect. At what point do they intersect, right? Where do those two lines touch and meet? And usually you'll be given the lines in algebraic form. You'll be given an equation for a line, not a physical line being drawn. And that's what these two are, right? These are the slope-intercept forms of two lines. Slope-intercept means that they have your slope, or the rate of your increasing, right? Rise over run, right? How much you're going up y versus every time you go over 1. And then your y-intercept, which is at what point you're on the y-axis. So for example, in this one I have a slope of 2, so I go up 2 and over 1 every time I'm increasing, every time x increases or decreases, every movement of x for one value of x. And then this one, right, -1. That means that that a point on this line is 0, -1, right? So this line touches the y-axis at -1. This one, right, a slope of -1. That means that, you know, for every unit or change of x, I'm going down 1 and over 1. And I have a y-intercept of 2, which means this line touches the y-axis at 0, 2. So it touches right here. And to find the point of intersection, which you'll also see called the solution, one pretty easy way is to just graph these two lines and physically see on the graph where they intersect. Now I'm going to do a rough drawing since I don't have it all labeled out, but usually you'll be given a graph or line paper, or worst comes to worst, you can do some rough labeling to try to find the solution. Right? So I'll start with red. Right, so I know I have a y-intercept of -1, so I'm going to start by putting a point at -1 right here. And then I know I'm going up 2 and over 1, and then up 2 and then over 1. And so I start to see, oh, I can draw a line. Actually, I'm just going to draw the line from this one. I notice I put arrows because we're continuing on infinitely, right? A line is infinitely long, so we need to put those arrows. And I'll do it for blue, right? We know I have a y-intercept at, say, 2, and I go down 1, over 1, down 1, over 1. I can draw that out. Right, and right now we can see, oh, we have our point of intersection at 1, 1. What does that mean? Well, remember, when we were graphing this, we were graphing the x's and the y's. And this is, in x, y coordinates. So their solution, their point of intersection is where x equals 1 and y equals 1. The reason why I'm saying this is that some problems may say, hey, what's the x value at the point of intersection? What's the y value at the point of intersection? And this way you can say, okay, my x value is 1, my y value is 1, or whatever it may be. And that's the basics of solving simultaneous equations by graphing. However, it's not the extent of it. There are some tricky things that some problems like to throw at you. For example, a common thing that problems do is that they'll put the equations for the lines in difficult forms, right? They'll have something like, 2x plus 2 equals, 2y plus 2 equals 4x, right? Something like that. You can't just go out and graph that. We don't have our intercept, we don't have our slope. But you can put it in a slope-intercept form using some algebra. This is really important. You can't graph it, but you got to say, oh, how can I put it in slope-intercept form? So what can you do? Well, in slope-intercept form, we have the y all by itself. No numbers or coefficients next to it, just y equals something, right? So our goal is to have y equals something, right? So have y by itself all on one side of the equation. So first thing I got to do is I got to get rid of that pesky 2. So I'm going to subtract by 2 on both sides. I have 2y equals 4x minus 2. I can divide by 2 to get rid of that 2, just so I just have y by itself, plain and simple. And then I have y equals 2x minus 1. And sure enough, isolating and solving, I get an equation in slope-intercept form. That's something I can use and graph pretty easily, and that's allow me to just go up and graph that and help find my point of intersection. That's another great strategy that you should use. Whenever you see a line that you can't readily graph, just say, let's put this in slope-intercept form. It makes your life a whole lot easier. But graphing isn't the only way you can solve simultaneous equations. It's a great one. It's nice and easy, and it works for almost any values. But sometimes you get weird functions or lines that aren't easily in slope-intercept form. They're in some weird, complicated form, and sometimes you just don't want to graph things. Well, I'll show you a couple other ways that can let you solve these equations without graphing them. So, let's say we have something like, I don't know, y minus x equals 0. And let's see, y minus 3x equals negative 4. Now, I notice neither of these two are in slope-intercept form. But I do see that, hey, if I add x to both sides of this equation, I'll just have y equal x. And I notice if I were to substitute y in for x in this equation, I have x all by itself, just terms full of x's on one side, and then a number on the other side. That means I could solve for x. So I'm going to do that. I'm going to take this in here, and I'm going to replace that y, or substitute that y, with an x, since we know y equals x. Right, so I'll have x minus 3x equals negative 4. That's negative 2x equals negative 4. And then I'm going to divide by negative 2. That cancels out the negatives, and I'm just left with 2. So x equals 2. And then if I want to find the full point of intersection, I'll substitute that back into my original equation and say, hey, y equals x equals 2, so y equals 2. So my point of intersection, my final point of intersection, is 2, 2. And there we go. That is our solution. We solve by substitution. And if that seems tricky, well, we'll do another one to practice. And this one is going to be a little difficult because it's not in convenient slope-intercept form either. In fact, it's even messier. Let's say we have, actually no, let's put it in slope-intercept form. Let's say we have y equals x minus 1. And then we have y equals 3x plus 1. Once again, we have to find their point of intersection. And here's where substitution becomes really, really easy. You might say, okay, slope-intercept form, they made it easy for me. I guess I should graph it. Well, you don't have to. We know y is equal to x minus 1. But we also know y is equal to this. So we know that these two things, this guy and this guy, have to be equal to each other, since y equals both of them. So what we can do is we can set them equal to each other. And we can solve them, right? So I want all my x's on one side and all my non-x's on another. So I'm going to subtract 1. And then subtract x. So I'll have negative 2 equals 2x. And I'll, of course, divide by 2. And I'll have x equals negative 1. What can I do? Well, I can take that negative 1, substitute it back into the original equation. So I'll have y equals negative 1 minus 1, just negative 2. All right, so my solution is negative 1, negative 2. There we have it. We've solved our equation. So as you can see, substitution comes in hand when I'm both given an equation that's in slope and intercept form, and when I'm not given an equation that's in slope and intercept form. The big thing is use it whenever you feel comfortable. If you feel more comfortable graphing, by all means graph. If you think this is easier, then use this strategy. It's entirely up to you. But let's do another strategy. One last strategy to show you how to solve these types of equations. And it's called elimination. Why? Well, because you eliminate other terms. So, let's go. And usually it's, so let's say I have something like x plus y equals 3. This is really messy. It's not in slope-intercept form. Don't like it. So that's too bad. But what if you have something like this alongside it? 2x minus y equals 3. Now this is just really, really bad. This is ugly. But I noticed something. If I were to add these two equations together, if I were to take them and add them, I'd have y minus y. I'd cancel out the y's. I'd just be left with x's and numbers, which means I could find the value of x when they intersect. Let's do that. So I add them together. X plus 2x is 3x. Y minus y, 0. 3 plus 3, that's 6. So I'm left with 3x equals 6. I divide by 3. I'm left with x equals 2. Once again, I can substitute x back into one of my original equations, and I get 2 plus y equals 3. I'll just subtract by 2 to get y by itself. And I have y equals 1. So my solution is 2, 1. That's how we use elimination. If that seems complicated, let's try it again. Let's do another example. Say I have y minus x equals 0 and y minus 3x equals 4. Right? Well, here I notice that I can't add them. Adding them doesn't really work. If I add them, I'll just be left with 2x's and 2y's, right? I won't be able to cancel any term by adding them. But if I were to say multiply this side by negative 1, if I had to multiply this entire equation by negative 1, I would have a negative y. And I can use that negative y when I add them to cancel out this y term. So I'm going to do that. I'm going to multiply this side by negative y. So I'll have, this will become, in fact, I'll just erase it. It's easier. This will become negative y plus x equals 0. And the 0 didn't change because anything times 0 is still 0. Well, with this, we can, heartily add them together. Negative y plus y, that's 0, plus x minus 3x, that's actually negative 2x. 0 plus 4, that's 4. So I'm left with negative 2x equals 4. I'm going to divide by negative 2. So I'm left with x equals negative 2. Once again, so I substitute it back into the original equation. So I have negative y minus 2 equals 0. Negative y equals 2. And we want to get y by itself. Divide by negative 1 to get rid of that negative sign. And I get y equals negative 2. So my final solution, my point of intersection, is negative 2, negative 2. So in that example, we had to multiply. And sometimes you'll have to multiply by different values in order to get it so that you can cancel. So you always have to be looking and you have to say, oh, well, what do I have to multiply by to get one solution for another? So let's see. Let's see. And here we have another equation. Let's say y equals negative x minus 3. And then we have y equals 2x plus 3. We're asked to find the point of intersection. So, seems difficult. Now we could do it two ways, and we can out of that say, oh, well, hey, why don't we substitute? Or you can also do something pretty nice. We can subtract them, right? So just like we're adding equations, we can also subtract them. So I'm going to subtract this entire equation. I'm going to have this negative sign. I'll just distribute to both sides of the equation, right? So this negative sign goes here. It also goes all the way over here, right? So in essence, while I'm subtracting this, I have negative 2x and negative 3, right? Because I'm doing, let's say, negative 3 minus 3, right? Just another way to think of that. I think about that. So y minus y, it becomes 0. Negative x minus 2x becomes negative 3x. Negative 3 minus 3, that's negative 6. I want to get x by itself, so I'll add 6 to both sides. Then I'll divide by negative 3. I'll be left with negative 2 as x. I'll substitute that back into my original equation. So I have negative 2. Of course, a negative is actually a positive. Minus 3. So 2 minus 3, well, that's just negative 1. So the point of intersection is negative 2, negative 1. And that is the essence of solving simultaneous linear equations. You have three strategies. You can graph them, you can substitute values that you're given, or that you can find, into other equations and then find the solution, or you can try to eliminate or cancel out one term, find the value of the other term at the intersection, and then plug that back in to find the other one. So you have three ways: graphing, substitution, and elimination. I hope you found this video helpful, and I hope you have a great day.